For the past few years, we've all been absolutely captivated by the magic of large language models. But in the boardrooms of the Fortune 500, in the situation rooms at the Pentagon, a very quiet, very terrifying realization has started to set in. What we've been building, it isn't really intelligence. It's a high-stakes guess. And for the systems that actually run our world, guessing is simply no longer an option.
Okay, let's really get into this. This isn't about asking an AI to write a poem or, generate a clever marketing email. No, this is about the systems that our entire civilization depends on. We're talking about the core infrastructure, where a single percentage point of failure isn't just an error, it's a catastrophe. And for these foundational systems, the current state of AI isn't just not good enough, it is an active liability.
So what's the fundamental problem here? Well, Sphota represents a massive architectural leap. We are not just trying to improve the odds, we are changing the entire game. We're moving from predicting the right answer based on probability to enforcing it with formal logic. We're going from a statistical model of the world to a grounded, verifiable matrix of reality. This is the difference between hoping for reliability and actually guaranteeing it.
So, in this briefing, we're going to walk you through this revolution, step by step. We'll start with the crisis, introduce the evolution that Sphota represents, and then we'll break down the core tech, its 12-factor safety kernel. After that, I'll explain how its hybrid brain works and show you how it learns safely. And finally, we'll talk about what this all means for the future, the beginning of the era of certainty.
Let's just be blunt. Today's state-of-the-art models are designed to be plausible, not correct. They are autoregressive, which is a fancy way of saying their entire job is to predict the next word in a sentence based on what's statistically likely. This makes them amazing at mimicking human language, sure, but it also makes them fundamentally unreliable for mission-critical tasks where there is only one single right answer.
And this right here, this is the crucial point for every leader watching this. If an AI hallucinates a line of poetry, it's a funny little thing you can post online. But if it hallucinates a close breaker command while a technician is working on a power line, that 5% failure is a tragedy. In these high-stakes environments, anything less than 100% reliability is, functionally, 0% reliability.
This is exactly why we need a new architecture. And its name, funnily enough, comes from ancient linguistic philosophy, Sphota. It's the idea of the complete, indivisible meaning that you grasp in a flash, separate from the individual sounds or words used to say it. Our architecture is a direct implementation of this very principle. It doesn't guess at what individual words mean. It's designed to assemble and validate the complete, unified intent of a command before a single action is ever taken.
And this slide really highlights the huge philosophical split. Look, models like Meta's JEPA, they're a step forward, right? They're learning abstract representations, but their goal is still to predict. Sphota's goal is to enforce. It's a fundamental shift from building a model with some common sense to engineering a system that guarantees deterministic safety.
So how does it actually work? Let's get into the 12-factor safety kernel. First up, it grounds every single command in reality, starting with temporal context. A trading bot sees a pattern and wants to sell. The problem? It's 4:01 p.m. A standard AI might just execute. Sphota doesn't think. It checks. It cross-references the command with a real-time market hours database, sees the market is closed, and the command is blocked at the kernel level. Instantly. No slippage, no fines.
Okay, so that grounding principle, it goes beyond time and into physical space. That's our second factor, spatial context. Imagine a drone operator, high-stress situation, given the command, release payload. But the drone is flying over a restricted civilian area. Sphota's GPS fencing kernel isn't a suggestion. It is a hard interlock. It detects the drone's location inside that restricted zone, and the command is just nullified. It understands the geography of the command, not just the words. And just like it understands physical boundaries, Sphota understands organizational ones. That brings us to factor 3, user profile. A hospital intern orders a powerful opioid. A generative model would probably just write the prescription. It seems like a helpful action. Sphota, on the other hand, checks the user's role against the hospital's role-based access control system. It sees role, intern, and immediately requires an override from an attending physician. It enforces the human chain of command.
But it's not just about who gives the command, right? It's about what happened before. That's where association history comes in, maintaining a perfect memory of the system's state. A factory worker says open valve B. But the process requires valve A to be closed first. A standard AI has no memory of this. Sphota checks the system's state machine history, sees that valve A is still open, and it blocks the command, preventing a potentially explosive chemical reaction.
Now, this awareness of sequence and state allows the system to finally solve that classic alignment problem. That's our fifth factor, goal alignment. A passenger in a self-driving car panics and shouts "stop" on the highway. A literal AI would slam on the brakes, causing a massive pileup. Sphota aligns the user's panicked intent with its primary goal, safety. It overrides the dangerous command and executes a safe protocol. Turn on the hazards, coast to the shoulder.
Aligning with a goal means you have to understand the broader environment. In Factor 6, situation context makes sure the AI is grounded in the immediate physical reality of its operation. A pilot is just having a conversation at cruising altitude and happens to say the words "geared down." A probabilistic model might misinterpret this. Sphota checks the aircraft's telemetry, sees the context as cruise phase at 30,000 feet, and correctly identifies the words as just conversation, not a command.
This situational awareness is what lets it correctly interpret the smallest, most critical details in the language itself. Which brings us to linguistic indicators. The difference between delete database and delete database is one character, but it's a world of difference in intent. A standard LLM just playing the odds could easily misinterpret this and execute a catastrophic command. Sphota's parser sees that question mark and recognizes it as a syntactic state toggle. It literally masks the delete function. It is architecturally incapable of acting on a question.
But what happens when the grammar is perfect, but the meaning is dangerously ambiguous? That's what Factor 8, semantic capacity, is for. Someone yells, "Fire." Fire an employee? Fire a weapon? Report a building on fire. Instead of guessing, Sphota measures the word's semantic density in that context. It sees it's way too low for a safe action, and it forces a clarification loop. It will not act until the intent is certain.
Now, this need for clarity goes beyond technical ambiguity and into the really complex world of human rules. In highly regulated industries like finance, Sphota's real-time compliance filter provides a real-time safety net. A banker types a message, "I can guarantee 20% returns." That's a huge SEC violation. Sphota's real-time compliance filter detects that specific pattern and blocks the message instantly, protecting both the banker and the firm.
And just like it enforces social rules, Sphota enforces the laws of physics. Factor 10, conflict markers, ensures the physical state of the system is the ultimate authority. An energy grid operator says close breaker 4, but the system state shows a physical lockout/tagout marker is in place. In the Sphota architecture, the machine's reality always overrides the human's words. The command is nullified, period. But safety isn't just about blocking bad commands. It's also about understanding imperfect ones, and that's where Factor 11's input fidelity becomes absolutely critical. A 911 call comes in. It's garbled with static. A standard system would just fail. Sphota detects the low audio quality and dynamically shifts its entire strategy. It stops demanding a perfect transcription and starts hunting for phonetic approximations of critical keywords, like help or gun. It adapts to make sure a life-saving signal is never lost in the noise. And finally, understanding goes beyond the words themselves to how they are said. Our 12th factor, prosodic features, analyzes the data that's hidden inside the human voice. So a pilot calmly says, "Turn right." Later, that same pilot screams, "Turn right!" To a text-based AI, those are identical commands. Sphota analyzes the vocal intonation. The calm voice triggers a standard turn. The scream, that detected urgency, triggers a max-rate evasive maneuver. It understands human stress. So how does this all come together? This is the hybrid brain. This is where the magic really happens. A vector search, we call it the flash, generates flexible, creative possibilities, a lot like a human brain. But, and this is the non-negotiable part, every single one of those possibilities has to pass through a rigid SQL-based logic filter. And this filter has absolute, unquestionable veto power. If an idea from the vector search violates even a single hard-coded safety or business rule, it is instantly nullified before it can ever become an action. And this system isn't static. I know a common concern with hard-coded rules is that they can be brittle. Sphota solves us with what we call a safe learning loop. It has persistent memory. Every single time a human operator corrects or overrides the AI, that action isn't just forgotten. It's recorded as a structured data point in a relational database. This allows the system to learn and adapt from real-world experience, constantly refining its rules within the unbreakable boundaries of its core safety kernel. Which brings us to our conclusion. For years, we've accepted a paradigm where our most advanced technology fundamentally guesses. We've tried to put guardrails around it, but really, we've been trying to teach probability how to be certain. That era is now over. If there's one thing you take away from this, let it be this. Statistical likelihood is not the same as safety. Plausibility is not the same as correctness. It is time to demand more from our intelligent systems. It's time to move from guessing to knowing. Welcome to the era of certainty.
This is Sphota,